It's 1 p.m. Let's try it again. Well, everyone, it's 1 p.m. Eastern, and that means it's time to begin our 87th CoCoRaHS Weather Talk webinar. Thank you for joining us today. I'm your host, meteorologist Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from the Colorado Climate Center at Colorado State University in sunny Fort Collins, Colorado. All of our Weather Talk webinars are sponsored by the I'm having a tongue twister here this morning. Generous donations of listeners just like you. Well, today's webinar will take a second look at atmospheric rivers. We welcome back our special guest, Marty Ralph, the director of the Center for Western Weather and Water Extremes, located at Scripps University Institution of Oceanography in La Jolla, California. Marty gave an extensive talk on atmospheric rivers. That's number 35 on our YouTube list if you'd like to go back and listen in on that one, back in 2014. But after 9 years, it's a good time to dive in on this subject once again, especially after last year's parade of atmospheric rivers along the Pacific coast. Marty is a leading expert on atmospheric rivers and provides input to policymakers on Western weather and water extremes. He is a leader in development of forecast-informed reservoir operations, working closely with federal, state, and local water managers. He is a fellow of the American Meteorological Society and has received awards from several organizations. Marty has a BS in meteorology from the University of Arizona and a PhD in atmospheric sciences from UCLA. Welcome, Marty. It's great to have you back with us today.
Great to be here. Thank you.
So as we start today's program, remind us again on how you became interested in atmospheric rivers. If I recall, it goes back to your younger days moving from Detroit to the desert Southwest.
You got a good memory. Yeah, I was a youngster, about 10, 12 years old, and we moved from suburban Detroit to the border country of southern Arizona, and I might as well have moved to Mars. It was before cell phones, and we had 2 TV channels, one in Spanish, and didn't get a lot of information like we have now at our fingertips. So it was very exciting. And I saw the monsoon rains, and I saw in Michigan, rivers have water in them. In southern Arizona, most of them don't, but they would go from dry to flood, and it was fascinating, and I've been hooked ever since.
Well, thanks, Marty. Well, we'll turn it over to you now, and we'll join you back at the end of your talk with some questions from our viewers out there.
Great. So I will set up my thing here so you can see. You see the PowerPoint slide now? Henry, you see the PowerPoint slide okay?
Yeah, it looks great.
All right. Well, great to be back. I watch CoCoRaHS online. It's amazing what you guys do, and citizen science is such an important thing. I really personally appreciate the effort it takes to put that in and online and to keep track of it. And having a rain gauge is one of my favorite things when I was growing up, to be able to see how much fell. And once again, that helped get me hooked in the field. Well, let me give you an update here. Compared to several years back, things have been evolving on the atmospheric rivers side of things, from the science to the observations to the predictions and all that. I'll give a slice of a few things here on today's talk. Well, first of all, let me set the stage by why we have the Center here for Western Weather and Water Extremes is partly because, frankly, the weather's different here than in the rest of the country. Much more variable in terms of annual precipitation. And you can see in this chart of the percentage of water year precipitation variability from year to year, variance, that's explained by the 7 wettest days each year. And it turns out that about in the southwestern U.S., particularly California, somewhere 80, even 90% of the variability from year to year is determined by what happens on those 7 wettest days. Not that they're back-to-back days. It could be any day during the year. I'm from Michigan originally, so that might be in the 40, 50% range. Much of the country has got half of that variability, from the 7 days. We have a certain climate here in the West Coast where summers are dry, so we really only have one shot at getting the precipitation each year for the most part, and it's in the cool season, we call it, which is basically fall into winter and somewhat into spring. But what are the types of weather that creates these wettest days? I think you know that the answer is atmospheric rivers, but let me show a little bit what that looks like in a modern case. It's a visible satellite image of, you guys have probably heard about bomb cyclones. This was a bomb cyclone off the West Coast about 2 years ago, and it looks spectacular. And you can see the low pressure center up here, with the wrapped up thing, and you can see the cold air clouds over the ocean here. But what's this looks like in the wind, when we look at what are called streamlines, imagine that's where, the wind's blowing along those lines. You see up here, the wind's coming out of the northwest, wrapping around the low center with that dark eye. And then down here, you see winds are out of the southwest, and there's a gradient in there. That's the cold front. And the purple is where the water vapor amount in the atmosphere is greatest. And notice how we have large water vapor content and southwesterly winds. That's where the atmospheric river is. The story of meteorology is that the low center up here is something, the cyclone center, meteorology is focused on for a century in many ways. And there's been a ton of vital work to help us understand how they form, to better predict them and the like. Sorry for the cough here, it's just a food thing. And the thing is that for many years, it was believed that if you got the low pressure center right, pretty much everything else falls into place in the forecast. But it just isn't really that way. The atmospheric river is about 1,000 kilometers away from the low center on average. And for these West Coast storms, where the AR hits is where the action is in terms of precipitation and often some of the biggest impacts. You can get really strong winds if this comes ashore. Often it doesn't come ashore, actually. It curls up and fades away before it gets too far inland. And down here, the ARs bring in tons of water vapor and rain and snow. Sometimes these cyclones will form farther north, and then the northwest is hit by the AR. So we've now been focused on trying to predict the AR, not just the cyclone. And you can get the cyclone right and not get the AR right. That's the basic idea. Why are these things important to the annual precipitation? Well, take a look at this example of what we call an arrow diagram. Each arrow represents the location of landfall and the orientation of the AR that was there at the moment it was strongest where it hit the coast. An AR hits the coast and moves up and down, it moves down the coast usually. So it's not like it just hits the one spot. But this is a good sort of shorthand for showing how many ARs there were and where they hit primarily. And the color of the arrow is based on the strength of the AR. And we now have a scale for ARs from 1 to 5, and it is based on intensity and duration. I'll show you that in a minute. This is the intensity part, and we have the different colors representing different intensities. Now, the color over land here is the amount of precipitation compared to normal in percentage. And the blues and greens, of course, represent wet. The yellows and oranges represent dry. And you can see a bit of a sparsity of ARs in the Northwest, and it's a bit drier than normal. And you see California getting hit, and ARs can penetrate inland. Turns out even in the high Rockies of the Colorado Rockies, on the west slope at least, about 40% of annual snowfall comes from AR storms. In the Sierra Nevada, which is right in here, it's on the order of 40% as well as snowpack comes from ARs. In certain parts of this region, half of the annual precipitation comes from ARs. Up here in the Northwest, it might be 30 to 40% of the annual precip. And it's not very many ARs hit a given spot each year, and those really add up. Now let's look at what happened a different year, the same 3 months, but a couple of years later. And what we see is one measly, a little weak AR hit California in that 3-month period. That is the heart of the wet season for this region. And you can see how dry it is from the red colors there. So left panel, lots of ARs, lots of rain and snow. Right panel, hardly any ARs, not much rain or snow. And here was the total deficit in precipitation for 3 water years. The yellow here is 1 to 1.5 years of precipitation short in a 3-year period. The orange is 1.5 to 2 years precip shortage. So like in this area, in a 3-year period, they only got half of the average annual precipitation they would normally get. Well, why are ARs important to precipitation? and this is a schematic, like a vertical cross section, and you see the ocean on the left and the mountains on the right, and the atmospheric river coming in. The wind is blowing up the mountain, and as it rises, it condenses water vapor and forms rain and snow, and that helps keep the landscape green. And then when the air goes over, it dries out as it comes back down and warms back up, and that's where we get deserts in the lee of the big mountain ranges. So this could be the Sierra Nevada mountains or the Cascade Mountains of northwestern U.S., or even the coastal ranges sometimes have they can have a bit of this effect. But the Sierras are up 10,000 feet and higher. The Cascades are 8,000 feet and higher, and then inland it's much drier. We call this orographic precipitation, and ARs are really the main driver of orographic precipitation in the winter on the West Coast. All right, now, how about globally? What do they look like? On the left here, we have the frequency of atmospheric river behavior, essentially in that red and orange colors. The reds are where we get ARs, quite frequently, and that the vectors are the strength of the IVT as integrated vapor transport. Think of like if that was a river, a terrestrial river, that would be like the cubic feet per second flow of the terrestrial river. IVT, integrated vapor transport, is the vapor version of that for the atmosphere. And you see the mid-latitudes here are red over the oceans and into the west coast of Europe, west coast of North America, west coast of South America, tip of Africa, parts of Australia, New Zealand. Major parts of the world are affected substantially by ARs. And on the right-hand panel, it turns out that we can look at it in terms of the frequency of ARs hitting the coasts around the world, and you see the bigger the red circle is, the more player it is, or the more frequent they are, and you get a condensed version of what I described on the left side. So that's wherever remember that orographic precipitation thing, or diagram. So now think of these places as being ones where if you got mountains there, in particular, you can get a lot of your annual rainfall from ARs. So it's a significant portion of the world. And notice also Antarctica down there. I'm not going to talk about it in the talk here, but there's an emerging understanding over the last several years that ARs play a vital role in Antarctic ice in terms of creating a lot of the snow that ends up piling up in Antarctica, but they're warm storms relatively, and they can also melt some of the ice in Antarctica. So that's a active topic of study. I won't touch on it here any further. Well, there also can be super problematic, of course, if there's too much rain too fast. It can cause things like this terrible debris flow, that hit Montecito near Santa Barbara a few years ago. More than 20 fatalities. Sadly, I went here afterwards a couple years later, and it was just amazing physically what happened, and tragic, of course, the loss of life it incurred. And we've been studying these ARs in terms of trying to understand their role in extreme precipitation, of course, but then also in flooding and in debris flows like this. And one of the things we've done is we've looked at the history over 40 years of FEMA, Federal Emergency Management Agency, records of flood damage claims in the Western U.S. And this diagram shows the dot size is the percentage of all flood damage claims over 40 years at that location or in that region that were attributable to atmospheric river storms. And you can see there are places in the West Coast that are 95, 98, 99% of all flood damages. When you look at it across the whole West, even farther inland, it's substantial in places. 84% of all flood damages in the last 40 years, or in a 40-year period in the West, were from AR storms. All right, so let's talk for a moment about the scale, the AR scale that we've created. First of all, it was created because as the AR topic became more, in the public circles, because media was interested in it, the science was interesting, and they seemed relevant. There came a time when the National Weather Service was receiving a lot of requests about, oh, is this AR that's predicted, is it going to be a big one or not? And there are different intensities and all that. So from that, it helped push me over the edge to lead the development of the scale from 1 to 5, and I'll explain it here. So this diagram on the left is the integrated vapor transport, that IVT, or cubic feet per second in the sky kind of number. And it shows the vector is the direction of the vapor transport, and the color is the strength of it. The direction is really important. Remember that mountain schematic, right? But if the AR is not perpendicular to the mountains, then there's less flux of water vapor up the mountain slope. So the orientation of the AR relative to the mountains is really important in determining how much impact it'll have. And if time permits, we'll come back to that at the very end of the session here. I've got a current AR. I want to show an AR outlook from our tools that's current. So the reds are strong vapor transport, IVT, and the arrows there are lined up perpendicular to the coast, which is basically perpendicular to the mountains and the Sierras. So that's looking pretty potent. Well, what do we do in terms of categorizing these things? Well, we've developed this scale, and we call it the AR ranking of 1, 2, 3, 4, 5. And what we look at is take a spot here on the coast, the black dot here, the Bay Area, let's say, and we look at the vapor transport at that spot over time. And we ask, when does the AR start and when does it end? The AR starts when that vapor transport, or CFS, in the sky gets over 250 units. And it ends when it drops back down below that. That's when the storm is passed. And that difference in time gives us the AR duration over that location. And then as it's overhead, we ask, what's the maximum vapor transport, or IVT, at the site while the AR is present? And that becomes the IVT strength. So you combine those two in this little matrix, and here you see, for example, if the AR hits and has a IVT of, say, 800, and it takes 36 hours to go overhead, that's an AR3. If, however, that stalls and lasts over 48 hours, we promote it to an AR4. That's how we factor in the duration. Or if it's shorter than 24 hours, we demote it to an AR2. In the hurricane business, it's become clear that the hurricane scale, the categories 1 through 5, have been really helpful for situational awareness over many years. However, they've got a bit of a gap in how it represents things, because it doesn't factor in the duration. In other words, if the hurricane or tropical storm stalls, and it comes with a lot heavy rain often, that stalling can cause serious flooding. This happened in Hurricane Harvey in Texas, of course, a few years ago, and Hurricane Florence a couple of years later in North Carolina, and then the others since then. So there's a reconsideration going on the hurricane scale to try to figure out how to deal with that gap. We have baked in from the very beginning that we have both the duration and intensity in terms of the AR scale. And I want to add that on the 1s and 2s, they're often usually pretty beneficial. And for water managers, it's important they know they're coming. But then if you've got a big AR4 or 5 is hit, and you get an AR1 or 2 like a half a day later, that's going to be more impactful AR1 or 2. So they're primarily hazardous or primarily beneficial, because it does vary from case to case. Well, then we took the economic analysis approach, and we calculated what the median damages are, and you can see how it goes up exponentially, essentially, with the ranking. And when we look at it in a different way, AR1s are mostly beneficial, often really helpful in water supply. Similarly for AR2s, when you get up into AR3s, you get a mixture of benefits and hazardous impacts. You get up to AR5s, these are often the ones that create, sort of the billion-dollar disasters. And if an AR5 hits an unpopulated area without much infrastructure, and it's early in the fall season when the soils are really dry, even an AR5 isn't going to cause a bunch of damage. It might actually be quite beneficial. But once you get into the heart of the wet season and the soils are moist, the rivers are already high, and the reservoirs are full, watch out when you get an AR4 or 5 coming. They can be really the ones that cause major damage. The ranking, the media is trying to call them categories. We're trying to get away from that and call it AR scale or AR rank really. And but you can see, the various Washington Post, CNN, Weather Underground, Fox, they're all using this terminology. And we do training for TV meteorologists as well, and they're using it. And we're building out, sort of educating the community about this phenomena and how it works and how the ranking works. So let's imagine for a moment we've got this storm coming in on the left, and we want to know what's going to happen in terms of the AR impacts. First of all, let's take a look at the fact that the AR part of the storm is not right where the low center is. The low center is over here, right? Like that one diagram I showed earlier. This is where the AR part is, and I'm just showing it schematically. Now imagine 24 hours later, I'm not going to move the satellite image, but schematically I'm moving the AR. And what you see is the AR is moving inland or to the coast and then down the coast. So that movement is part of what we have to try to predict. But also the AR can be amplifying or strengthening or weakening. And those things all happening together make it complicated to show a single image that explains what's going on. So part of the benefit of the AR scale is we can condense that all into a color dotted diagram for the coast. And each dot represents over the next 7 days what the maximum ranking on the AR scale is predicted to be at that location on the coast. The inland color fill is the precipitation forecast, but focus on those dots. And you can see quickly, intuitively, oh, it's the Bay Area. The orange dots are where the AR4 conditions are likely to be. And the yellows are AR3, so watch out there. But down in San Diego or up in Seattle, AR1s. So this is a significant storm. And this is one that ended up having a lot of impact because it came on the heels of 2 other really big storms. And sadly, there was quite a lot of flooding with this one. But this is our equivalent for ARs of what's called the hurricane cone of uncertainty diagrams, where they show a sort of V-shaped thing where it gives you uncertainty about where the hurricane is going to hit shore. This is our West Coast version of that because ARs are essentially the high impact storms of the West. The TV media is also using it in some cases like this, highlighting it in their 5 or 7 day outlooks. NASA has decided to include it as a major element, ARs as a major element of a cool display at their headquarters, which I just went to last week. I happened to be in DC. It was amazing. It was, you walk into a dark room and it shows globally how the Earth looks from space. And they spent about 25% of their whole display period talking about atmospheric rivers. And they did it with this very cool video graphic that you're surrounded by. Excuse me just a second. Okay, so let's turn for a moment to the ARs of this winter. All right, so New Year's Day brought big storm to the West Coast. The color fill there is the water vapor in the atmosphere. The winds are the winds at about 5,000 feet above ground. And you can see the winds blowing the water vapor on shore and the long, narrow nature of the strong water vapor signal. That's the AR. When we multiply the wind by the water vapor, we get the IPT, or the cubic feet per second in the sky. And by the way, if we were to cut across the AR right like this and imagine calculating then the flow of water vapor towards the coast in the AR, this is a strong one. On an average AR, that water vapor transport is the equivalent on average of 25 Mississippi rivers, what they dump into the Gulf of Mexico at a given moment on average, 25 Mississippis. Also 2.5 Amazon rivers. Amazon is the largest river on Earth in terms of discharge into the ocean. So atmospheric rivers are literally the largest rivers of water vapor in the world, or of water and fresh water, and they're in the form of vapor in the sky. And where that hits the coast is exactly where we get the heaviest precipitation. This diagram on the right is the 24-hour precipitation from National Weather Service map. Some of your guys' data might even be in there. And you see some places the yellows are over 8 inches of rain in 24 hours. This was a major event for flooding, and you can see the correlation between where the AR hit and where the heaviest precipitation is. We see this time and time again now. We know this is how it works, and it helps us in our prediction work because we know it's the AR that you have to forecast to get the extreme precip right in the West. I'm having a little bit hard time with the cough here. I'm going to have to take a pause for a moment. Stand by.
While we pause, I'll give a brief plug real quick to attend our webinar tomorrow on the new CoCoRaHS Data Explorer. If you click on the message of the day in the left-hand menu of the CoCoRaHS homepage, you'll see a link to register for tomorrow's webinar. Again, a tutorial on using the new CoCoRaHS Data Explorer.
All right, I'm back. I have given hundreds of presentations. There's a handful where I've ever had to stop. Sorry about that. So here's water year 23 in total from through April. And you can see how heavy the precip was and the frequency of the ARs hitting California. Guess I got to click on this to get the arrow to work again. There we go. And here's what happened in a 3-week period where we have an onslaught of 9 ARs in 3 weeks, 6 of which were strong or greater. That's normally what we would see in an entire winter across the whole state of California. We had 6 largely focused in the center part of the state. And that led to a major improvement in the water outlook for the state. We also see ARs are where we find most of the big sort of traditional damaging impacts of weather. For the West Coast, a lot of these damages happen, from storm reports and all you can get from Weather Service in ARs. And this onslaught of 9 ARs over 3 weeks, there were over 1,500 local storm reports documented by the Weather Service. So there's also a nice set of papers. There's a nice paper that shows that the vast majority of the watches, warnings, and advisories in the cool season on the West Coast are in the context of atmospheric rivers. So in other words, for situational awareness, if people know there's an AR coming, there's a better possibility to be aware there could be the sort of more traditional damaging type conditions we find with weather generally. Now, this is a diagram that shows a new forecast tool we've developed over the last several years. I probably showed an early version of this in 2014 when I spoke, but we've been using it regularly ever since. People seem to love it. The diagram on the left is essentially looking out 16 days. You go from 1 day lead time here on the right side to 16 days on the left. This happens to be the ECMWF model, the European model, which only goes out 15 days. We can flip between the two and see the US model, which goes out 16 days. This is a probabilistic diagram, and where you see these reds, oranges, and yellows, that's where we see more than 50, 60, even 80 or 90% odds of an AR hitting. So like in this spot where it's purple, we've got every one of the 50 ensemble members of the European Center are predicting at least a minimal AR is going to hit this position on the coast. I don't know why that went forward. There we go. And if we go to this one, you see it at 7 days lead time, that red is about, 80, 90% chance that an AR is going to hit the Bay Area, 7 days ahead. And remarkably, and we rarely see this, we saw a really strong signal in the forecast models, even out as far as 10 or 12 days of this sequence of 5 or family of 5 ARs in a row. And this was, there'd already been a couple big ones hit, and these were on top of that. This diagram is part of what was displayed at the Flood Operations Center for the state of California every day for the people responsible for doing evacuations or preparing for potentially, flooding and the like. This is now part of the system for monitoring and predicting, storms on the West Coast. And on the bottom right, you see the AR scale. I think I covered that before. That diagram on the right is also presented regularly. The state of California Department of Water Resources shows these products in real time from our center as part of their online tool, WaterWatch. National Weather Service also refers to these tools in their briefings to the public, oftentimes in the West Coast. You can see an example of that very same diagram highlighted here in a Weather Service briefing from last January, or the January before, actually. Now let me turn to one of the things we're doing to try to make the forecasts as good as they can be. And the U.S., as you probably know, has long had for several decades a hurricane airborne reconnaissance program, where weather reconnaissance aircraft exist in the U.S. arsenal for weather at NOAA and at the U.S. Air Force Weather Reconnaissance Squadron. That one's in Mississippi, the NOAA one's in Florida. And they have for years been able to fly hurricanes to help make the forecast better. Because that's largely in the summer and fall, and ARs on the West Coast are in the winter, a few years ago, I proposed that we use those aircraft to fly atmospheric rivers off the West Coast. We call that AR Recon. And that has really taken off, and no pun intended, from just having a 2-week trial period in 2016 to 4 weeks, then a couple of years later to 6 weeks after that. And now I'll show you what we did last winter. First of all, what is it? This is a schematic. It showed up in the Bulletin of the American Meteorological Society on their cover. And it shows an AR schematically is this orange blob with the translucent sort of thing around it. ARs are focused in the lowest 10,000 feet of the atmosphere, and they're a few hundred miles wide and a couple thousand miles long. And you see the vector there, that's showing the vapor transport heading towards the coast. This thin gray thing up here is there's often clouds above the AR. Clouds are wet and they have upward motion a lot of times. So there's a cloud top there, and that disrupts several of the key types of satellite data that we would prefer to have go all the way through, but the clouds stop that. Some actually goes through still, and yet there's still a huge gap in data out here. There's hardly any observations in the AR above the ocean surface that can be used in data simulation models. So we go out with the Hurricane Hunter aircrafts, the Air Force C-130s, NOAA's G4, and we drop these sensors called dropsondes with a little parachute. And I might have one right here in just a second. Yeah, here it is right here. This for scale, you can see it with my holding it up and all. And this is a parachute that pops out when it gets into the air. It's released from the plane. There's temperature, moisture, pressure sensors here, and the drifting of it in the wind is recorded through GPS, and that gives us the wind profile. It's remarkable technology, really effective at measuring with high vertical resolution. And we go across these ARs, and here you can see 4 different transects where the dotted yellow lines are where we're dropping them. And we try to cross it as much as 4 times, and we're slicing and dicing it. It's like getting an MRI of the AR. And we get that data then back to the airplanes. They process it there and then send it via satellite communications down to the ground to the big data bucket for weather models, where all the global models take the data out of that to start their new forecast. And we're also experimenting with GPS satellite radio occultation. I won't go into that. And then we have drifting buoys that are deployed by NOAA for tracking ocean currents and sea surface temperature. And we're adding pressure sensors to some of them as part of AR Recon to leverage their being out there already for temperature and ocean temperature and currents. And on the left here, you see all these publications. We're very much a research and operations partnership between our center, CW3E, and NOAA's NCEP and the Air Force Weather Reconnaissance Squadron. But we make sure that the results are peer-reviewed, scientifically sound, and show quantitatively how these work and demonstrate the impact. So this has now grown substantially to this winter. We had 39 IOPs, which is IOP is a day where we flew at least 1 airplane. We try to fly 2 per day. And we did this now for 5 months with a few gaps around the holidays. And what we're really looking for ultimately is 60 days in the winter where we can fly at least 1 aircraft out of the West Coast. And these data are making a big impact in the forecast skill. This is what the AR onslaught looked like in terms of 13 consecutive days of AR flights. And then this one is actually for the whole winter. And you can see the flight track on the left here with the dots over the AR. And you can see the aircraft here on the right. Here's an example of the impact the data make. Here's what was observed. The color fill is the precipitation amount. The purples are the heaviest. Here's what we predicted when we included the National Weather Service model, included our AR recon data. It predicted something pretty close to reality. And when we excluded the AR recon data, the model didn't get that at all. This was the most important impacted area of the storm. And you can see how important these data can be in an individual case like this. When we looked at it through the whole winter with NCEP, the National Weather Service, and we looked at different domains, geographic domains, the California domain, where we were trying to make the improvements the greatest, we saw a 12% improvement in the heaviest precipitation. This is 1 inch and 2.5 inch thresholds. The lighter precipitation amounts are here, were improved as well, but the heaviest is where the most improvement was. And this corresponds to about a decade of model improvement. In other words, all the work it takes to improve the weather model, like the physics of it and how it runs and what its resolution is, we did that with one new data set. And this is now an average over many cases. And there are a couple of papers published now from the previous year's version of this. So this is really a part of the weather prediction arsenal now. It's been developed around the AR concept and the idea that to get the precipitation right, you've got to get the storm that produces it right. In the West Coast in the winter, that's the AR storm, or ARs are those storms. We're also experimenting with this radio occultation I mentioned on the left. The aircraft has a sensor that sees the satellite set over the horizon, like the GPS, navigation satellites, and the beam of that signal bends with refraction through changes in temperature and moisture in the atmosphere, and we can extract information that goes into the models. And on the left, you see all the different tracks of that data that came with the dropson data. So think of the dropsons as being vertically slicing below the airplane, and this radio occultation is looking out to the sides. So they complement each other beautifully. And on the right, we see the dark area is this is a map, of course, see Hawaii in the middle here. This is where AR alley is. Basically, the most frequent AR occurrences are where the darker the gray is. And the dots are where there are buoys out there, drifting buoys I mentioned earlier that have, in some cases, AR recon. Well, these are all the AR recon enhanced buoys. The buoys would largely be out there already, just doing ocean temperature and currents. We're adding, the sea level pressure to it, and that's very helpful as well. In addition to the aircraft-based soundings, we're also deploying radiosondes, where you launch a balloon that then pulls, carries the sensor upward. And each of the lines here, each of these lines is a different radiosonde ascent. We did 133 here from just west of the Sierras, 113 from the coast. Here's one from an island off of LA, from the mountains near LA, and from San Diego. And the dates are color-coded here. So all total, I think we did, a few hundred different launches over the course. I guess it would probably be 300 or 400 over the course of the winter. These are great for diagnosing what's going on and understanding whether the models are getting it right or not. We're also providing these data for assimilation into the forecast system. And traditionally, when the balloon goes up, it's transmitting the data by radio back, and then that upward profile goes into the forecast models. We, however, have started also once the balloon pops and the sensor drops, it's still recording. And instead of stopping when it recording the data and all that and transmitting it when it pops, we keep recording it on its way down. So we sort of double the value of that one sounding. And we're using these data also in assimilation into the models. Also, we've developed a specialized version of a weather model. It's regional and it's tailored to predict ARs best. It is now the most accurate model, and it embeds in the global models like the GFS model from NOAA or the ECMWF model, and then we run a regional domain where we tailor it to get the ARs right. We don't have to worry about getting hurricanes right because it's not a thing out here on the West Coast. It really isn't. We had an exception to that, one very rare one here in San Diego, which was cool to be part of, but it just doesn't come close to what these ARs do. And the fact these lines are dropping down to the right means we're improving that model over the years since we started the center. And that improvement is rapid by normal standards because we're focused on one season, the cool season, and one storm type, ARs, in one region, the West Coast. And it's made a big difference in the forecast skill. In addition, we are, of course, as everybody in the world seems to be doing, looking at AI or machine learning, artificial intelligence. And the graph on this left is showing over 7 days lead time that the red line, the purple line is lower than the red line. The purple line is after we use artificial intelligence on top of using the model. We apply the artificial intelligence to the GFS model forecast, or GFS, and the root mean square error, RMSE, decreases. And that's about a 20% reduction in the error of the IVT. That's what this parameter is. This is essentially the AR forecast skill, and it's showing a significant improvement. So better observations from the AR recon and the radiosondes and some other things I didn't mention. And then also from a better model, and then machine learning on top of it. This is our formula now, the playbook for improving precipitation forecasts, extreme precip across the Western US. I'm going to skip this one for a moment, except it's pretty cool. We're doing it on time. Yeah. So, well, on the right-hand side, you see that yellow line in the middle. That's what's called a narrow cold frontal rain band. Do you remember that sad debris flow event on Montecito I showed earlier? This is the type of storm that produces it. This is very heavy rain rates, like up 3 inches an hour sometimes, but they only last like 15 minutes. And believe it or not, the area where that precipitation is forming primarily is in the lowest, like 5,000 feet of the atmosphere. And when the NexRad radar beam is up here at 10,000 or 15,000 feet, it has a hard time seeing that. And the left-hand diagram is the NexRad view of it. The right-hand side is we put in a special radar out here, a smaller, cheaper radar that's super good, as part of a program where we're putting 6 of them in around the Bay Area to try to detect this type of feature. The red areas are where there were wildfires, sadly, a lot of them up in this area north of the Bay Area, and where an NCFR, narrow cold frontal rain band, overlaps the burn areas where you have the highest chance of those debris flows. Where the NCFR hits an urban area, even without the burn area thing, that's where you get the most likely to have urban flooding. And that's what this storm did. So you can see with the new radar data, it's possible to have a better look, a better able to see the specific phenomena that causes it. And this is the size of the radar. You can see the engineer there is assembling it, and the crane strap there holding the radar. You get a sense of the size of the antenna. Here's the network that's going in. It's about 2/3 deployed now. And then how am I doing on time? I got a couple minutes left. So let me just go back to this one for a second. This type of radar is called a gap filling radar because the NexRads are super important to our country. And we have about 100 and some odd of them around the country. In some areas, the coverage is really good. In some areas, it's not quite as good. In the Bay Area and the West, often because the big radars, the NexRads are put up on mountains more or less, so they're not blocked by the mountains. They get to see over the mountains. But quickly, the radar beam gets too high, and you don't see things like that narrow cold frontal rain band unless you're real close. It happens to be real close to the NexRad. So these are a radar type that's on the order of 10% of the cost of the big NexRads, and we can put a number of them out in the same region, roughly, or between NexRads to fill in the gaps. And there are 2 types called X-band. This is an X-band, and C-band, which is a slightly longer wavelength, which is a slightly bigger antenna. And those combined with the NexRad are under consideration for deployment around the country to fill gaps in radar coverage in the mountainous West and in areas where underprivileged communities have had less coverage of radar per normal. Finally, let me close with just a couple things here in slides, and then I want to go to a forecast thing real quick online. So one thing we're doing is we're trying to work on innovations for soil moisture. We don't really have enough time to cover that. Sorry, I don't know why that's not advancing. There we go. You probably heard about Lake Powell's been in trouble. Well, this is what happened in the last 5 years. Lake Powell dropped by half. And now it's dropped even more this last year. And when you look at that drop, it lost 60% of its volume in those 5 years. It's pretty obvious you can't keep doing that for the next 5 years and expect, unless we get lucky with inflow. We did have a good wet year last year, but there's a lot going on to try to improve predictions of this inflow into Lake Powell. And one of the things is soil moisture, which is highly variable soils here. I won't go into that anymore here. Before I turn to the forecasting thing, well, let me actually turn to the forecasting thing here real quick. I'm going to do that and that and that and that and that. All right. Here we have one of our products from CW3. It's a forecast, or in this case, analysis from the US model, the GFS, looking in the Pacific Ocean, and the ARs are that yellow and orange and red colors. And that's today. And now we look at it, we'll just watch it progress through a week of forecasting. There's an AR hitting the northwest. Another one looks like it might, but then it fades. And now we got something developing offshore. Let's let it go one more time, and then I'm going to stop it towards the end. And here we see that coming ashore. That's the US model. Now we can look at the European model. See, there's differences there, and that's typical. Let's let it keep going. And now let's look at this storm. No, let's keep going. Let's look at this storm right here. That's about a week out. And here's the European model. They're both showing a storm, but very different positions. Those differences are like a storm hitting Oregon versus Washington versus British Columbia. If we look now at a given point on the coast, right up here in the upper right here, you see the red dot. So this is for a point on the coast there of Washington. And now we're overlaying over a 10-day period all of the 80 different forecasts from the US model and from the European model. Each of those gray lines is a different forecast of the AR, the IVT, at that point over the next 10 days. And the dots show where the highest value is in that 10-day period. And you can see how the green dots are a little to the left of the purple dots. It's showing about a 12-hour difference in the when it hits. And then the purple bold line and green lines are different by about half a ranking of the AR intensity. And then notice these thin gray lines out here with a few dots. Some of the ensemble members are showing this storm isn't as big in the forecast, whereas about 7 or 10 days out, it's much bigger. This is a new type of display we've developed here that's used regularly now. And you can see if I go down the coast what that looks like. I'll wrap up here in just a minute or two, Henry. And now we're looking at another new display for AR scale. And this is in the same location roughly. And this is the US model. And this is 14 days on this map. This is the previous 7 days. And this is the ranking of the AR essentially, strength-wise. The color fill is the ranking on the scale. So there was an AR1, 2 of them hit on the last few days. And now there's an AR3 in the forecast. Here's our matrix, and you can see the letter C there is for the third AR in this 14-day period. And you see it's just barely getting into the AR3 level. So it's just a marginal AR3. But if we go to the European model, let's see what it says. It says AR4, but once again, just barely into AR4 because of duration. So we have this display system now. It's easy to look at different ways of seeing these forecasts, and I encourage you to take a look if you want online. And then one last one is we have our subseasonal to seasonal predictions that go for week 1, week 2, and week 3. Let's look at 3 weeks lead time now. At 3 weeks, we're not worried about what day the AR hits or it's active for ARs. And what we do is we calculate the anomaly. So here with the US model, down here in the bottom right, the blues mean more than average AR activity. So the northern part of the West Coast, the US model says above normal AR activity. If we go to the ECMWF model, it says below normal AR activity. And if we go to the Canadian model, it shows well above normal AR activity. So we're seeing a difference was 2 of the 3 models are going with more active AR conditions in the northern part of the West Coast. One, the European model, is going for less. And last year, when we had that onslaught of ARs, I have to let you know that 2 weeks ahead, we saw signals that were very in line with each other for the onset and then for the cessation of that onslaught, 3-week-long onslaught of ARs. All right, let me close with that there and go back to the PowerPoint for 2 last slides. First, I want to acknowledge that what I'm presenting here is largely a result of work of our team here. This is our CDB3 team, and there's a number of colleagues from around the country who joined us for our annual meeting. Some of them are in the picture too, but we have a very diverse group of individuals from different disciplines, different stages of career, different interests, all working together to try to improve our understanding of Western weather and water extremes and to provide new tools and forecast methods for seeing what's coming. One of the things we'll do, I think, given your emphasis in CoCoRaHS on precipitation measurement, we have a product. If you go to our website at CDB3, and no one's nerdy enough to have that acronym, so just Google CDB3 and we'll come right up. We issue what we call a rainfall category alert when there's rainfall that exceeds 8 inches in 72 hours in the Western U.S. and particular West Coast. And then if it's over 12 inches, it's an RCAT 2. If it's 16 to 20 inches, it's RCAT 3. If it's over 20 inches, it's RCAT 4. And these then show up as a map. In this case, it was one that hit in Southern California. This was a year or so ago. I just happened to have it handy. But sometimes we'll see 20 dots on the map here. So if you want to see where the most extreme precip is, this would be a good way to do it. And I think, Henry, there might be a way to connect with the CoCoRaHS community to develop a version of this display for our center to use that is based on CoCoRaHS data. Finally, I'll leave you with this slide, which shows cover of a story in Scientific American on atmospheric rivers that I wrote a year or so ago. And it's really a short, concise story about a lot of what I've shared here, plus some more about how it's used in water management. And here's contact information, and thank you very much.
Marty, thank you so much. That was, wow, very informative and a lot of questions. Folks, if you want to send in your questions, we'll try to get some of them in here. Marty will try to answer them if we don't cover them. I got a couple quick ones here for you. And we see this is West Coast generated, most of the stuff here. How frequent East Coast, Gulf of Mexico? Do we see atmospheric rivers, the time of year for those? And the second part of that is that do you do the AR numbers for the East, or is it just for the West Coast?
Great questions. Yeah, there's been quite a bit of work over the last several years from different universities, different folks looking, including our group here, looking at ARs elsewhere in the country, and they do affect the Midwest or the Great Plains. There was a really terrible storm in Nashville in 2010 that we studied that showed a very strong AR hit there, stalled for 2 days, and billions of damage, sadly loss of life. And then nor'easters actually in the East Coast come in sometimes with a pretty good AR, and where that AR hits and how it is oriented relative to, say, the mountains in New England or the Appalachians really influences the extreme precipitation that occurs. So yes, they are a thing elsewhere in the country. We're in the process of developing some of these tools and applying them in those regions. We're not ready to, post those quite yet. We want to make sure we do a good job on developing them and understand how they work and what their constraints are. So yeah, it's the seasonality varies, but I think that the Nashville one was in May of 2010. The New England ones with nor'easters are often in the winter, and there can actually be ARs at other times of year as well. There's some papers on the Southeast U.S. From NOAA that have shown that also. So that's where we're at on those.
So Marty, one other quick one here. People that are not familiar, live in parts of the country where they really don't get an AR. what is it like? Is there a lot of wind? Is there a lot of lightning? Is it like one of these squall lines coming through, or is it just a steady rain that comes? What do we see if I'm got an AR predicted, it's coming
Yeah.
in? What would I experience as looking out the window?
Well, it really depends on where you're at. In the stronger ARs, it's a region of strong winds, and it's also lots of water vapor, so it can be it's very humid, and we'll get sort of long, steady rain with heavier bursts embedded. And if one of those narrow cold frontal rain bands forms, that'll bring like a 15-minute burst that does a lot, can create a lot of problems. So usually not much lightning. It's not really, convection or thunderstormy type weather, although there can be some. So they also tend to be warm storms. So if you're in a place where there's mountains or whatever, you might be more likely to see rain higher up than snow. And then when the cold front goes through and the AR passes, it gets colder and the snow level drops to lower altitudes. Those are some common situations. And you can get big waves, with them because they have a long fetch over the ocean oftentimes and can bring in, major surf.
Thanks. So Anne asked earlier on on one of your diagrams, you have an IVT magnitude on one of the axes. What does that stand for?
Integrated vapor transport, IVT. So if we take a layer, say from the surface to 1,000 feet, and we have the wind in that layer, and we know how much water vapor is in that layer, we can calculate how much water is being, how much transport of water is happening in that layer. Then if we go to 1,000 to 2,000 feet, the same two numbers, water vapor content and wind, and we do that all the way up to about 10 kilometers. We add all that up vertically. That's the integrated part, integrated vapor transport. So the total above you in the atmosphere that's moving horizontally.
And really quick to cut in, this is Noah with headquarters here. We had a few people chime in on the chat and I answered them already, but Marty, on your slide with those the intensity ratings, the vertical axis actually lopped off the 1 as it went higher and higher. So it appeared to go from 750 back down to 0. And then so a few people asked what was going on with that that vertical axis, but it did appear correct on your website, just not on that slide. So that's just a quick thing for those who noticed.
Yeah, sorry, the 1 got cut off in the slide, not on it's 1,000 is what that would have been. And the 1 just was too far over for the visual to capture it.
Marty, thanks. Can you send us any links
while you're doing the next question? Go ahead.
Yeah, can you send me a couple of links that might be helpful for folks to look at these? We'll put them on the website as well from your webinar for additional sources.
Can do. I just want to show you guys how to find some of this information very quickly. One particular thing. So this is our website cover page. You just search CW3E, you'll find it. Under forecasts, go to this AR1. And one of the coolest things I think is this diagram right here. This is a map. You can find the IVT maps in forecasts for different domains. There's the West Coast, there's the whole Pacific, and here's the Eastern US. So you can actually, if you're elsewhere in the country, you can see the whole continental US with our IVT charts. And here's one where you can even, you can advance it with your arrow, or you just put your cursor on it and click the space bar and it'll loop on its own. And you can see here something coming into New England at the end there. You can see hurricanes have a lot of vapor transport. This one's coming into Mexico. And so you can see this in different parts of the country. You can also go to, here's the West Coast one I showed you. And then one more, here's the Atlantic. So you can see Europe in this domain, if you're interested in that. And then just going back to the cover page, you can actually go to these links right here and just click on that landfall tool. Here's the AR scale landfall map, and here's a precipitation forecast map I didn't have time to show. So anyhow, there's a little bit of navigation there. And then one last thing I want to show is one of the challenges we have is when we When we look at the vapor transport, even with the AR scale calculation, we don't factor in the direction of the vapor transport. And if the direction is parallel to the mountains rather than perpendicular, then we don't see as much precipitation as we might think. And let me show you an example of that in this forecast here coming up. All right, so here we go. All right, so see here, the vectors are coming out of the southwest, south-southwest. They're not really perpendicular to the coast here. So the amount of precipitation in much of the Cascades will be less than we would get if the storm was cut, if the vapor transport was coming in perpendicular. So just wanted to share that nuance here.
Yeah, that's great. Do we have time for 2 quick questions that have come in? If we
can go fish longer, yeah.
Bill in South Carolina wants to know, does the jet stream have an effect on movements and intensities of ARs?
Yeah, the jet stream and ARs are intimately connected. The jet stream is up high in like the 30,000 foot range, roughly, super high winds, sometimes, well over 100 miles an hour, even up to 200 over the Pacific. And the AR's down low, below 10,000 feet. And it has winds sometimes in the 50 to 100 mile per hour range, just a few thousand feet above the ocean. The thing about the jet stream aloft is the air is super dry up there because it's so cold. So it's not, even though the winds are strong, it's not transporting much water vapor. Down low is where the water vapor transport's happening because the winds are strongish, not as strong as up high in the upper level jet, but still very strong and very moist. The upper level jet also has a role dynamically to influence the vertical air motions that can take that water vapor down in the AR and move it upward so it can condense and form clouds and precipitation. So when those two link up in the right way, we see what's called the warm conveyor belt, where the AR is then lifted, and partly through the influence of the upper level jet, and that lifting helps focus the precipitation over what's called the warm front, which many people probably know. And anyhow, there's a whole 3-dimensional schematic thing on that. But good question. Yeah, they're connected.
And here's one from Fred. He wants to know, what is the correlation between AR frequency and intensity with the ENSO phase? So La Nina, El Nino, how does that work?
Great question. If I had $1 for every time I've had that question, we'd be having some special technology here. But anyhow, it's more complicated than we've been thinking. There's been a lot of intuition that on the West Coast says El Nino is very wet in California, so therefore there's got to be a lot of ARs as part of that. And La Nina is very dry, so not enough ARs. Ironically, what we've seen in the last 20 years is with the big La Ninas, we've had in Southern California at least some very wet years. And it's because we've had a number of ARs somehow get in despite there being a La Nina. And in El Nino, not always as wet as expected over the last few cycles, and it's an absence of ARs. So ARs appear in Southern California, at least, to be the disruptor of the correlation between ENSO and precipitation. We haven't examined that in other places yet, but our preliminary results are showing some indication towards that. Stay tuned. It's not published. It's just early analysis, but really important question and one that's come up quite a lot.
Well, Marty, we want to really thank you for a very informative webinar today, and great to see the updates from when we talked last time. Again, maybe we'll have you back another 10 years from now, and we'll look again at where we're at this point. But thank you for taking time. You have a busy schedule as a director there, and again, most appreciated. And we'll try to, our CoCoRaHS reports, I think, help you guys the best we can to see what has fallen where. And so folks out there, keep measuring, because you never know how your report can help these guys with as they do their research on ARs.
Exactly. And I want to say thank you, Henry, and for everybody involved in CoCoRaHS for your volunteerism. And I just remembered, I want to tell a quick anecdote. 1990-ish, I'm in LA at grad school, and I've got my rain gauge and went out for an evening and got back, and we had gotten, I think it was 4 inches of rain overnight in LA. And that was in the middle of a drought. And it turned out to be half of all the precipitation for the whole winter came in that 6-hour period. And it was remarkable. It left a big impression on me. It has been part of why I do what I do today. And it was because I had a rain gauge. So great to see CoCoRaHS doing well, and encourage everybody to continue because we really need it.
Well,
Back to you.
that's a great story. I appreciate that. Okay, folks. So, yeah, thanks. As we close out today's program, we want to let you know that our next webinar talk, our Weather Talk webinar, will be taking place on, get your calendar out now, Thursday, December 14th. So almost 2 months from now, when Dave Robinson of Rutgers University will take a look at snow and the many aspects that come along with that wintry subject. We'll have registration up shortly on our website where you can sign up for that. And we hope you'll join us for that. And so again, before I forget, when signing off today, please take the survey. They'll pop up on your screen. Always helpful for us. So until we meet again, this is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now. We hope that you'll join us again this December.